So now we move to practical applications. We will start talking about PCA and continue next time. So PCA, which is principal component analysis, is very popular technique to reduce dimensionality of your data of any kind. So you might have all kind of features, all kind of numbers, vectors, whatever the data are. You have too much of it. You want to get rid of some of the unimportant parts, which are not explaining your phenomenon, whatever you want to describe. So you want to get rid of some of the dimensions. Okay, they might be just noise, but you cannot get rid of them because they are all interconnected in regular rectangular system of coordinates. Especially if you have like 500 variables, you have no idea how they are interconnected, correlated in some way, or so on. So you want somehow to decorrelate them. So you want to find system of coordinates where they will be mostly decorrelated. They will be orthogonal to each other, all the dimensions, right? So you don't want the original system of coordinates, you want to transform it to different system of coordinates in such a way that all of the variables will be independent of each other in that new space, in new system of coordinates. This is the overall idea of PCA, and this is how you do that. Okay, so you have technique for that. Let's say you have two-dimensional, for simplicity, I'm showing that in 2 dimensions, just to give you some geometrical intuition. You have some bunch of points, which are, let's say, 2 features that you're describing, you experiment with, like length and area, whatever. So you have distribution of one, distribution of others, and lengths of and areas of particular objects might correlate somehow. So you might have some diagonal relation, maybe negative correlation, like here. I'm familiar with correlation a little bit, right? What correlation means when I'm saying correlation. Have negative correlation relation here. So x-axis and y-axis are dependent in terms of data. Okay, so if x goes larger, y goes smaller. This is what negative correlation means. You want to decompose it to completely separate variables, which will be x tilde and y tilde, where x is changing independently within that same, and y is changing independently within that same. Which means practically you want kind of that ellipsoid to rotate it like that and to position it that way, that it will have some variability here and some independent variability in other dimension, completely independent, orthogonal, okay? It will be much easier if you're doing, for example, classification of the things. It will be much easier to put some threshold in PCA space compared to that space, because here everything is dependent. You cannot choose particular subset of points. Let's say, I don't know, let's say this 3 points or this, whatever, 6 points are one class, these are other class. Like how would you put threshold here to differentiate between these points? But if your axes are like looking that way, which are more diagonal, then I can just put threshold here above these 2 points. It will be a single number which is classifying one group versus another group. You need only one threshold for that. It's much more easy to do in PCA space. So you also want to get rid of some of the dimensions. And if this distribution along that axis of that ellipsoid is just noise, because it could be noisy measurements of something, right? And the main variability is in that direction, you care only about that variability and you don't care about that variability. So you want kind of to squeeze it to a line. And this is how you reduce one of the dimensions. You practically kill the noise and squeezing that ellipsoid to a single line and projecting all these points on that line. That's what PCA does eventually. Okay, so let's get to the actual practice. How you get them. Generically speaking, you have n-dimensional data points. Let's say you have n features. Okay, we'll call them x, y, z, and so on, some numbers. All right, we will organize n data points in the matrix. Again, columns are features. Each row gives you particular feature vector with numbers. So you get some sort of matrix m by n. Any questions on that? What it means? You have particular measurements from a particular object, let's say, again, length, area, whatever features you want in computer vision, or it could be something else in some other areas. And these are different objects, okay? Each point is different objects, different vectors. Now, what do? You find a covariance matrix of that V tilde. And what is V tilde? V tilde is each column is normalized by its own mean. You're subtracting mean from each column. What does it mean to subtract mean from each column? You're just shifting that entire thing into the origin mean. So the mean of each column will be 0. And this is how covariance is defined. It's like value minus mean times value minus mean. That's how you compute covariance, okay? So this matrix will be same thing minus mean of itself. And you multiply and transpose of that matrix by that matrix, you get covariance matrix. That's how covariance is defined. So if you know a little bit of statistics, you've seen the formula before multiple times. But if not, I'm just defining that for you. And my goal is not kind of to make a professionals of PCA developers or whatever. It's just to give you an overview of like how this works in general. Practically, on the main diagonal of that matrix, you will have all the variances of each one of the columns, which means it's like covariance of vector with itself will give you the variance of the vector, all right, which is standard deviation squared. And then we will find eigenvalues and eigenvectors of that matrix C, which is covariance matrix. This is what PCA does. This is a procedure. We will sort them in descending order, and this order will tell us importance of each dimension, which means smaller the eigenvalue is, less important that is. It's like more noisy it is. You don't care about these dimensions. So eventually you'll be able to replace them just with zeros. And we'll do the same thing, by the way, with singular values when we'll learn about them. So you can sort practically dimensions by importance, just based on how much each eigenvalue is scaling that space, because this is what it does, right? The size means like how much you stretch the space. The more you stretch it, more important it is, in a sense, okay? And this will show you, like eigenvectors will show you principal directions which are more important than others. So the ones which correspond to bigger eigenvalues will be more important. And the idea is, okay, so I think that we can go through examples next time. Just remember the overall procedure, how we go through that. And next week we will continue talking about like how you actually do that in MATLAB and so on. Any questions? All right, thank you. All right. Good morning, everyone. How are you doing? Good. Any questions on the previous lectures? Okay, hopefully this week I will publish another assignment for the lab, including all of the power methods and other things that we discussed. But today we will continue talking about applications of eigenvectors and eigenvalues. And hopefully we will get also to another topic, which is singular values. These topics are very connected. Practically singular values are extension of eigenvalues for non-square matrices. So the overall idea is that they will have similar applications to what I'm showing here. And I will show connection a little bit later, but now we are talking only about eigenvalues and eigenvectors. And I will apply this theories to all kinds of applications. We started to talk previous time on principal component analysis, PCA, which is very popular. So who has used that before or heard about that before the previous lecture? PCA, it's a very popular method in data analysis in multiple complex domains. Dimensionality reduction. Some of you at least heard about that, but now we will see how it actually works. And I will not get into too much detail. In MATLAB, it's like one liner in MATLAB, so it's very easy relatively to implement it in MATLAB. But we will see what does it do, how you can do that, and what is the result. And here is the idea. Okay, so overall idea is that you have some cloud of points. This could be some sort of features. They could be multi-dimensional features. It means you have practically vector of numbers. Let's say bunch of medications that you're testing on a bunch of patients. Okay, and you want to see which medication works the best or contributes the most to healing process. So you have matrix, which is rows with the particular patients, columns with the particular medications, but you have too many of them. You want to reduce the number of these features, these medications. They want to see only the dominant ones, the important ones somehow. And yeah, it doesn't have to be medications. It could be any kind of features, anything that you can put numerically. okay? Any numerical features. So you want to have less of these features because you want to train your machine learning algorithm or whatever regression analysis or whatever you're doing with the data. You want to have less dimensions. You don't want that many features because, let's say, in clinical studies, we have typically a lot of clinical variables like age, height, all kind of other parameters, clinical parameters of blood tests and other things. So you have like 1 million different variables that you need to handle. Most of these variables are irrelevant for your questions that you're asking, right? So you don't care about particular things. They do not affect anything in your results, but you don't know which ones are which. Like, should you use a particular variable of age? Will it somehow correlate to the outcome or it will not? You typically just don't know that. So you need to get rid of that variable somehow. So you need to identify if this variable is important or not that important. Or can you get some information from that huge number of vectors, data vectors, and shorten it to smaller number of dimensions. So this is the overall problem that we are trying to solve, like how you simplify your problem, how you ignore something which is practically speaking noise. This is the idea, okay, of PCA. And when you have this representation of points, and if you're looking on the blue circles here inside of the ellipsoid, these are just data points with 2 dimensions, which is very simple, but it's very difficult to draw that in 100 dimensions. So it's just very basic idea. So these points are showing you practically x-axis and y-axis, which are 2 different features, whatever they are. Could be length, area, or age and height, or all kind of features, okay? Something numerical. So coordinate of that point, single circle, will give you set of features. In more dimensions, you will have just more features, all right? So you want to classify these points into one class and another class. You want to separate them somehow, but they oriented not very conveniently, diagonally somehow, okay, in that cloud of points. So PCA, what it does, it rotates it in such a way that it becomes more or less aligned with axis. This is what it does. So it actually identifies axis with which it will be aligned, which means the axis which will look probably diagonally like that. It will be aligned with that cloud of points. So it finds that angle of the axis. And if you remember, this is exactly what happens when you're computing eigenvectors. These are those axes which are aligned with the input data in a sense. So you'll see what we actually do, what is the procedure to get there. And after that, the next step is to squeeze some of the dimensions, to ignore some of the dimensions, which means, let's say we want only one dimension out of these 2. So we want to figure out what is the most dominant feature out of these 2 features, most important feature. And this is corresponding to dominant eigenvector and eigenvalue, which is like biggest stretch direction of that ellipsoid. And this ellipsoid again could be n-dimensional, so it could be stretched in all kinds of dimensions, 3, 5 million dimensions, whatever. So you're looking for the biggest stretch in particular dimension, and you want to ignore most of the other directions, right? So what you do, you're practically having those axes one will look like that, another will look perpendicular to that in 2 dimensions, right? So just squeezing that entire thing into a single line, which means that ellipsoid will squeeze into a line connecting these 2 points. So these points will be projected on that axis, orthogonal projection of all these points to that axis, and you practically will have only one dimension in PCA space, only that single axis. It will be all points on that axis. That's it. This is the overall idea of PCA. This is what it does. And you can squeeze more dimensions if you wish. Like if you have 500 dimensions, you can squeeze almost all of them. You'll be left with a few dimensions, and everything will be projected into these dimensions from all of the dimensions, so you practically will ignore all of the other dimensions. But you will ignore it in particular order, which means that you will ignore only the dimensions where you have smaller variability. So it's not really explaining your signal, it's mostly noise. So it's fine to ignore that kind of dimensions, all right? You're not ignoring the biggest one or second biggest one or whatever number you need. Okay, so here's how you do that after classifying some vectors. So you have some vector matrix of vectors, actually, x, y, z. Each one of them is Rn. So these are your feature vector. and it has some n values, n numbers, whatever they are. And you can organize multiple vectors as columns stuck together in particular matrix, which you will call V, right? Doesn't matter how you call that matrix. Some matrix where you stack all of the data points. So you'll get particular big matrix, all right? We compute, as we mentioned previous time, covariance matrix of that. And for computing covariance, you're subtracting mean from each column. And then you multiplying dot product pairwise, all of the vectors, which means x1 with x1, x1 with x2, x1 with x3, and so on. In that case, it will be x with y, x with z, and so on. So you kind of dot product all of the pairs. So what do you really get? What is a dot product? If you remember, intuitively, dot product tells you how similar some vectors are. Okay, so bigger the dot product is, more similar the vectors are. This is the overall idea behind it, especially if one of them is orthonormal. So it's like unit vector. Then it's actual correlation between two vectors. Okay, if you dot product two vectors, you get correlation between these two vectors. How correlated they are, all right? So this matrix practically showing you correlation of mean normalized vectors, which is exactly the definition of covariance matrix from, if you learn that in probability theory. Again, if you haven't learned statistics or probability, just believe me, this is covariance matrix, okay? This is how you compute covariance matrices. So it will be V transpose times V, which is all of the pairwise multiplications of the vectors x transpose x, x transpose y, x transpose z, and so on. So you'll have all of them, and on the main diagonal, you will have variances, which is kind of vector with itself, right? On the other parts, you will have covariances of these vectors, technically, okay? And this is how you compute that new matrix, which you'll call C, covariance matrix. Any questions on that? Okay. So we find eigenvalues and eigenvectors of that matrix C. And pay attention that this matrix has to be symmetrical because x dot y is the same as y dot x for any two vectors, right? So you can switch the order in dot product. So it has to be symmetrical. It doesn't matter which one you multiply by which, okay? And for symmetrical matrices, all of the eigenvalues will be real eigenvalues, okay? This is additional theorem that I haven't mentioned, but now I mentioned that. So for symmetrical matrices, they are very nicely behaving. Their eigenvalues are all real. And this matrix is also kind of having only positive or zero eigenvalues, yes, because it's like square of the matrix. So for square of the matrix, all of the eigenvalues are positive practically. And this is why it's very convenient also to order them in particular order. So you'll have smallest one and biggest one, not like regular eigenvalues where they could be complex and you cannot really order them in any way. Because complex numbers, you cannot find like order or rank of some kind. For real values, you can order them in just decreasing order or increasing order. So this is that kind of case where you actually can order and rank eigenvalues by importance or stretch, how much they stretch the particular direction, all right? And as before, eigenvectors of that matrix will show you those axis directions, and eigenvalues will show you how much you stretch in that direction specifically. And that stretch will be completely independent for each dimension, which means each dimension will have their own, not singular, but eigenvalue, okay? And this is by how you stretch each direction, and they are orthogonal, so there is no problem with stretching them separately. Okay, yes?
The question is, why do we first have to compute the covariance matrix? Why don't we just do eigenvalue decomposition, pick the dominant?
You cannot do eigenvalue decomposition on the original matrix. It's not even square. It's not even defined for the original matrix. So here you want to see. So PCA method is telling you how much of particular dimension describes variability of particular variable and their intervariability between the vectors, okay? So this is the matrix which is showing you how much each pair of the vectors covariable, right? This is what covariance is, right? Covariant, like how much they covariant, like how they dependent on each other, okay? And if they are independent, they are orthogonal, completely independent, right? But they could be also very correlated. So you want to decorrelate them in eigenspace. So you're looking for such orientation of X's where all of the variables will be completely decorrelated or orthogonal to each other. Okay, so this is the overall idea. And in that space, it will be much easier to manipulate or to classify or do other manipulations on the vectors, because each component in the new PCA space vector will be completely independent from each other component. They will be orthogonal, right? So they will be independent in a sense. So I'm looking for that independent space. All right. Okay, so we will sort the eigenvalues in descendant order from biggest one to smallest one. And eigenvectors will show us principal directions, which are the main directions. And let's pick some example. You have two vectors of numbers, whatever they are. And these are two features. And these are just samples of these features. It would be like 35, 100. Second one will be 45, 91, and so on. So you'll have like pairs of numbers for each pairs of features. Again, it could be like length and area, whatever it is. All right, so you can plot that as those blue points, and you'll build matrix V, which will be, I think, 15 by 2. You have 15 numbers, I think, and you have 2 columns. All right, so this matrix, you compute mean of each one of the columns, subtracting that mean, what it does to your cloud of points. So pay attention, the original axes are between like 40 or negative 40 to, what the number is? Yeah, so from 40 to 110 on the y-axis and from 20 to 80 on the x-axis, right? These are the axes that you have right now. When you're subtracting the mean, obviously everything will be centered around origin, okay? That will be from minus something to plus something on both axes. So it's all the cloud just moves to the origin. Okay, this is what you do by subtracting the mean. Now, second step, you're computing the covariance matrix, which is V transpose V, after you subtracted the mean, all right? And each value here in the main diagonal will show you variability in X direction and Y direction. So the top one is 271, this is variability of points, variance practically. This is variance, okay? Statistical variance of these points in that direction, and statistical variance in that direction is very similar. Okay, it's like 289, because it is oriented and you can see the axis almost square, right? And this is not good for us, because if you're looking at that cloud of points, it's like very stretched in one particular direction and not very stretched in other direction, right? So we don't want these variances to be almost equal. In PCA space, we want the second dimension to be as squeezed as possible, all right, compared to the first direction, which is dominant direction, principal direction. All right, and this is what this transform will do for us. So what will happen, you will have one of the eigenvalues will be 12, another one 548, like huge difference, all right? And this is because that direction is huge, and the second one is different. And this eigenvalues will tell you like how big they are, all right? This is a proportion ratio between the green line and that yellow line, okay? This is ratio of these eigenvalues practically, yes.
The C describes the yellow line and the green line.
No, C describes overall variance in that direction, variance in that direction, and cross variances between the two directions, which is practically negative 268. It's like, you know, because of the slope, they are anti-correlated, right? The X and Y are anti-correlated because they are having negative slope. Not positive, like if you know regression, right? In regression, that slope is positive and that slope is negative. So they are anti-correlated. If one goes higher, the second one becomes lower. Okay, so they are like opposite correlation connection. So this is why the number is negative in covariance matrix. But this is talking about Z space right now, okay? That's before the rotation of the ellipsoid to align it with the axis. This is the original rectangular coordinates as we used to see, okay? So in this rectangular coordinates, this matrix is not great, okay? We want that matrix to be diagonal, ideally, okay? We want to have only variances and no covariances at all. If covariances will be both 0 on the non-main diagonal, then the vectors are orthogonal. That's what it means. Like dot product between X to Y will be 0. This orthogonal vectors, right? So we want diagonal matrix, but this is not even close. And this is why we need PCA to make it diagonal. And eigenvectors exactly doing the diagonalization, right? So you will have, after the transform of eigenvalues, you will have diagonal matrix, and this axis will be aligned with that ellipsoid, all right? So S1 is definitely smaller than S2, and you'll have corresponding eigenvectors. I'm not computing them, obviously, but you can use MATLAB or whatever, or you can compute it even by hand, but these are the eigenvectors of that matrix. And again, if you're looking on the green vector, it's negative and negative, so it's looking kind of down here from the origin. Okay, this is the arrow, and this is already normalized to have norm 1. And the second vector will be looking like negative and positive, which is that direction. This is a yellow one, all right? So these are two eigenvectors that we get from that matrix. And they show you like which direction you need to look at as dominant direction or principal direction. So what will happen, you will just multiply that matrix V by those eigenvectors, which is matrix of eigenvectors, and you will get that red orientation of the red points from the blue points. Okay, so each point will be multiplied by that vector in that matrix. And you will kind of rotate that ellipse and put it like that. So this will be your single dominant direction, and everything else will be squeezed. So now, using only red points, it becomes much easier to squeeze it, because all you need to do, you just put in all of these points, projecting that on zero line here. And you'll be left with only one dimension. Like previously, with the blue points, it's like difficult even to understand how you project to something. Like if you project them here, they're all very variable. And if you project them here, they are also very variable. So you cannot get rid of one of these dimensions, right? Because it's like you're losing a lot of data if you kind of squeezing it that way or squeezing it that way and projecting on one of the axes, because they are all over the place. But in that orientation, in red orientation, you can easily squeeze it like that, and you will have all of them only on y-axis. Let's say you have one dimension. All right? And this is how you do that in MATLAB. So coefficient will have PCA, this function PCA. You put in that matrix, in that case, X is V, okay, your original data matrix, and computes for you entire principal component coefficients as a matrix. So you can read description how you do that, or see examples how you do that in MATLAB. It's very simple, okay? You just giving that single line command and gives you all of the orientations like that already as we compute it here. So you'll get it with one line of MATLAB, all of the PCA coefficients that you need for your new vectors, all right? And they already will be sorted in the order of importance, which means farther away you get, less importance it becomes, like less variability you will have in that vector. So you can just replace them with zeros and then transform it back, right? So you'll have all kind of small numbers, replace them with zeros, remove these vectors, get back to your original space. It will be kind of squeezed, and all of these points will be aligned on a single line instead of 2 dimensions, practically speaking. So this is how you reduce dimensionality in general. Any questions? All right, so who have heard about page rank algorithm? Any idea what that is? It's actually
something websites.
Yeah, this is actually Google stuff. This was a publication from 2 students from Stanford, somewhat famous now, who established a company named Google. All right. So this paper was pretty old paper, and started in this paper we present Google, a prototype of large-scale search engine, blah, blah, blah. Okay. And the paper was from 1998. And clearly, these are one of the most rich people in the world now, okay? So this algorithm, this eigenvalue that they used cost approximately $25 billion, okay? This is how important eigenvalues are, okay? So the idea that they had is that you can rank pages by a very simple principle. And this principle is if many pages point to your page becomes more important. Practically almost that's it. But you have additional twist here. And the twist is if important pages now point to your page, it becomes even more important. Which means if some big important page have hyperlink to your page, then your page is important. More important than if some unknown page points this hyperlink to your page. So it's like having bigger value to it. Because like if big university pages or big company pages pointing to your particular page, probably you have something important on that page, right? This is the overall idea, as simple as that. And you can use eigenvalues and something kind of similar to PCA, because again, you need some sort of ranking by importance. And if you're doing ranking by importance, you can say like, well, this page is more important than this page. And when you're doing Google search, all of these important pages are jumping on the first page. And less important pages, less important web pages are later in Google search. This was that huge deal where they started to rank pages by importance and defined importance using Google matrix, which was really big deal. Obviously, one of the biggest companies now in software field, billions and billions of dollars income out of that simple algorithm. And we will see how eigenvalues help us to compute that kind of thing, all right? So this page rank algorithm, practically what they proposed, is offering you some numerical value, which is rank numerical value of the page on the web, okay? And again, it's measured only by hyperlinks on other pages which are pointing to that particular page. That's it. This is the only information they care about. How many hyperlinks, what kind of hyperlinks, from where the hyperlinks are coming. That's it. This is how it works. So higher ranked pages typically appearing on top of Google search, and they interpret importance as link from page A to page B as voting of page A for page B. All right, this is kind of single vote. And depends if page A is important, it will give more weight or less weight to that importance of page B. All right. So here's how it works in general. And you can think about those smiley faces as particular pages, okay? And different pages pointing to some other pages. So pay attention. Let's say this yellow page pointing only to one page, but this is a super important page, yellow one. Why? Because so many pages are pointing to that page. You see all of these hyperlinks are pointing to that yellow face, which means it's super important. And it points only to that red one, right? And nobody else pointed to red one. So red one is pretty big, and size is importance in that case, coded by size, right? So red page becomes very big because yellow page, which is huge, points into it. And it doesn't matter that nobody else points to it, okay? But let's say smaller page points to that green one and nobody else points to that green one. So it's still small. Why? Because it's much smaller than this one, because this page is smaller than this one, right? And those pages are not pointed from anywhere, so nobody cares they are tiny, right? Nobody goes to these pages. Nobody cares, right? If somebody points to that page, this page becomes larger. And this page points to that page, this becomes larger. So they're kind of interconnected within all of that communication between the hyperlinks from page to page. And this is if you want your page to be ranked higher, if you have any web page, make sure that some big sites point into your page and point to your own page from other web pages, okay? This is how people grow the popularity of pages. They just point, they have like hundreds of different pages and they cross-link all of them and they all become big, okay? Cheating, but it works with that algorithm, right? So people know how to game the system in a sense. But if you get somebody like university, for example, which is big player in that game, pointing to your page, this is a big deal. It becomes much more popular on Google search. If some big company like Microsoft or Google or some other big corporation points to your page, this becomes a big deal, because then it jumps immediately to the top ranking in your Google search. And not only Google is using that now, so it works with some modifications. They modified it a little bit, obviously, through the years, trying to prevent all of this cross links between friends, prevent cheating a little bit. So they modified it a little bit, but the core of all these algorithms is still the same. Okay, how many hyperlinks you have? Okay, so here is our idea. The node importance increases as it connected to another important nodes. And we will have some example how it works. So node 1 connects to node 2, 3, and 4. Node 2 connects to other nodes. And this is how it will look like, okay? So let's say you have 4 different websites. And it, by the way, can work not only with websites, it can work with any importance ranking problems, okay? So you have these 4 websites, and as you can see, they're all pointing to each other, so it's bidirectional. In that case, this is a simplistic case. You don't have, for example, arrows from one to another, but not backwards. Just all of them are bidirectional. This is just connectivity problem. And typically you can solve that kind of problems in brain analysis, let's say, where you have connectivity, and you can rank connectivity by importance, like what connections are more important than some other connections, using the same technique, practically speaking. So as you can see, most of them are connected to 1. Okay, so 1 connected to 2, 3, and 4. So this node becomes very important, pretty big. Okay, node 2 connects only to node 1, so it's tiny. Nobody likes it. Node 3 connects to node 1 and 4, and node 4 connects to node 1 and 3, so they are kind of similar. Their situation is similar because 1 points to 3 and 1 points to 4, and 3 and 4 point to each other, so they are kind of equal between them, okay? They have similar weight. All right, so what we start with is something which is called adjacency matrix. And this is used a lot in graph theory and many applications of graphs to all of these things. So adjacency matrix says what nodes are connected to what nodes. And each column will be like node 1 connected to 2, 3, and 4. Node 2 is connected only to 1. Node 3, like look by columns. Node 3 is connected to 1 and 4. And node 4 is connected to 1 and 3. Okay, so you put 1 wherever it is connected and 0 where it is not connected. Okay, this is what adjacency matrix is. And this matrix describes the entire graph. This is all you need to know about connectivity in that graph, right? So this is connectivity matrix practically. It tells you where it is connected or disconnected. 0 disconnected, 1 connected. Any questions on that? All right. So you're taking normalized principal dominant eigenvector of that, which will be whatever that vector is. And these are the values of importance already sorted in such a way that bigger number in that vector will be like more importance to that page, okay, or to that connection, whatever. So clearly the biggest one here is 0.61, which means page 1 is, and we're talking only about absolute values here, so it doesn't matter if it's positive or negative. So 61 is the biggest one, right? So node 1 is most central. And node 2 is least central because it connects only to 1. So it's 0.28. This is the smallest one, smallest magnitude, all right? So this is how you can sort any number of pages. And all you need here is only one dominant eigenvector, like where is the biggest stretch, all right? And if you remember power method, this is exactly what it computes. So you don't need to do through computation of all of the eigenvalues, eigenvectors. You need only one. You just iterate, and you can iterate on huge matrices. It doesn't matter. They have like billions and billions of web pages, and the matrices are sparse. So it's very easy computation in that case. And you iterate on that kind of matrices. This is what PageRank does. Okay, it computes just dominant eigenvector, sorts that eigenvector by value, by absolute value. And this is how you see your search results sorted by these numbers. But there is more than just that to Google algorithm, okay? So this is super simplistic backbone of that idea, but this is not really Google algorithm, so it's a little bit smarter than that. So here is what they actually use. So they use eigenvector centrality measures, which are similar ideas to that thing, and I will talk a little bit about that. And this is the theory part of that algorithm. And here's what we actually do, okay? So for n nodes, network of pages, we defined hyperlink matrix. And this is not exactly connectivity matrix, but like something between the adjacency and probability. So we give every page 1 divided by n, and n is total number of connected pages. So it's like probability to jump to a particular page. So they think about users now, okay? So each user can go from particular page, let's say page 1, to 1 out of those 3 pages in that particular plot. It could go to 2, it could go to 3, or it could go to 4. We assign equal probability to each one of these jumps. So you'll click on that hyperlink from that page. So it will be 1/3 for each one of them. So it's like adjacency matrix, but instead of ones, you have probability of jumping into that particular page, all right? So from page 2, like nothing, just all zeros. You have no probability jumping anywhere, you're stuck there. And this is a big problem for Google, initial Google search. And this is how they solved it, okay? So instead of saying, well, you're stuck on that page, if your robot, which is comes, you know, that these are kind of robots which are crawling to different pages and searching hyperlinks. So if your robot, which is searching for your new page, stuck in a particular page, you jump from that page to any other random page. This is how it works, which means that you practically assign each probability here instead of zeros as 1 divided by n, and n is number of pages. Okay, so it can jump anywhere. So the idea is that user will just switch to some other random page if you don't have any hyperlinks on particular page. Again, whether it's true or not, it's a different question, but this is what Google assumes. All right, this is what this algorithm is doing. It says, well, we'll replace all of the columns of zeros with 1 divided by n, and n is number of pages. That's it. Okay, same thing with number 3, so it can jump to 4 or it can jump to 5. So it's 1/2 4 and 1/2 5, and so on. So each page will have their own kind of probability here. And now, pages with no outgoing connections, problematic, and we will replace them by 1 divided by n. And we will call that matrix, after we modify that h with 1 divided by n, we will call that matrix S. All right, just remember the name, because we'll use it in the next slide. So here's how you think about that. They provide particular probability that someone may decide not to follow any link on the web page, but to go to some other page, okay? Also possible. You don't have particularly to go like from link to link to link to link, but you have some probability just to switch completely different place, right? So what they propose to do is something that they call Google matrix, and this is a G, which is alpha times the previous matrix S plus 1 minus alpha times matrix E, where that entire matrix is 1 divided by n values, like random place anywhere, practically speaking. So what is alpha times something plus minus 1 minus alpha times something, when alpha is between 0 and 1? Do you know what that is? This is actually a very popular approach. Many different things are doing that particular thing.
Better value?
Sorry?
Better
What is that?
in probability by something, times by something.
So it kind of relates to probability, but it's not exactly probability, okay? So what that is weighted average between one value and another value. You can think about that as low-pass filter of first order. This low-pass filter of first order, and alpha is that coefficient of how much you give weight to the first element versus the second element. So let's say if alpha equals 0.85, which is typical for that particular algorithm, okay, you can choose any number between 0 and 1. It means that in 85% of cases, you expect that to go with the first matrix, and in 15% of cases, you are going with the second matrix, practically. So it's weighted average between the two matrices in terms of probability, okay? But it will sum up to 1 always, because 1 plus 1 minus alpha will, alpha plus 1 minus alpha will be always 1, right? So the sum of the weights is always 1. So it gives you kind of percentage of weight to each one of these matrices, matrix S and matrix E. Like completely random matrix, not random, completely even matrix, I don't know how to call it, for E, and your original connectivity matrix, and which is coming from H through S, and you weight in them, which means that you assume that probably like in 85% of cases, you will click on the links, but in other 15%, you will just go somewhere else. Okay, this is the assumption. All right. So importance of each page is defined by its centrality based on the dominant eigenvector, eigenvalue of the matrix G. Okay, so you're just using the power method on that. And that power method, you're just iterating to find that dominant or principal eigenvector. And you sorting it, and you get all of your results done, practically. This is how you get things done. And here is a MATLAB code which is implementing that. So pay attention, I already simplified here a few things. So that matrix G, you can write that way, okay? And here, the matrix, the vector E will be vector of 1 divided by n elements. So it's like all of the 1 divided by n. Again, n is number of pages. And V is n by 1 vector with ones where you have no hyperlink in particular pages. That will be 1. So if you multiply that thing, which is V by X, it will have only 1 divided by n in particular place in the dot product, right? So kind of, it's almost like index vector, shows where the pages with missing hyperlinks are, all right? So this is how you define that kind of thing, and you will get back something that we showed here, right? Okay, so we went through that. And then you have that MATLAB code, which is practically implementing that iteration. And here I'm using 9 iterations on that thing. And eventually you will get that kind of result for these pages. Okay, this will be your dominant eigenvector. And clearly you have very different values. Let's say obviously 2 is very low, as expected, because it's not not many pointing to that 1. But 1 is pretty strong and 4 is pretty strong, but the strongest one is 4 because many of them are pointing to that 4, especially from important vectors, important nodes like 1. Okay, so 1 is important, it is pointing to 4, so 4 becomes even more important. And 3 is important also as well, it points to 4, so it becomes even more important. So overall, it becomes kind of one of the most important ones, and 5 becomes the most important because important 4 points to 5, and 3 points, which is important, points to 5. And this is kind of linking that to the biggest value of 0.3 compared to other values. All right. So this is how this overall algorithm works. Any questions? All right. So this is the end of the eigenvalue and eigenvector lecture.